Welcome to the Deep Dive. We're your shortcut to getting genuinely well-informed on the topics that matter, cutting through the noise. Today, we're taking a journey into a critical part of our digital world, web application security. It sounds technical, but it affects everyone. Our guide for this is the OWASP Top 10, specifically the 2021 list. Now, OWASP is the Open Worldwide Application Security Project, and this list, it's hugely influential. It's based on real-world data from tons of organizations, thousands of apps. It tells us the 10 most critical security risks we really need to understand. So our mission today is simple. Unpack these 10 risks. We want to see how they actually work, look at some real-world examples, sometimes pretty scary ones, and, crucially, figure out how to defend against them. This is essential info if you use or build anything online.
Exactly. And you might be thinking, okay, tech stuff, why me? But the thing is, these vulnerabilities aren't just, theoretical. They are everywhere. They get exploited constantly, and the impact, well, it can be massive. We're talking huge data breaches, serious financial hits, loss of trust. This really is about protecting our data, our systems.
Okay, let's dive right in. First up, A01.2021, broken access control. This one topped the chart in 2021, found in something like 94% of tested apps. 94%. So what exactly is this? Is it like having the wrong keys?
That's a pretty good way to put it, yeah. Fundamentally, broken access control means the application doesn't properly check if you, the user, are actually allowed to do what you're trying to do. So using your key analogy, maybe your house key suddenly works on your neighbor's door. Or maybe it even opens the bank vault downtown. It's about permissions gone wrong. We usually see a few flavors of this. There's horizontal access control failure. That's where, say, user A can somehow see or change user B's data.
Like looking at someone else's shopping cart.
Exactly. Or maybe changing an ID in the web address, the URL, to see another user's profile page. Then there's vertical access control failure. That's when a regular user, maybe like you or me on a site, manages to get access to admin functions, stuff they absolutely shouldn't be able to touch.
Ooh, okay. Like accessing a control panel.
Precisely. And then there's contextual failure, which is a bit more subtle. Maybe you have permission to edit your profile, but a flaw lets you edit any profile under certain circumstances. The context wasn't checked properly.
So you mentioned changing IDs in URLs. Is that like insecure direct object references or IDOR, where you see orders 1, 2, 3 and just try orders 1, 2, or 4?
Spot on. IDORs are a classic example of broken access control. Super common. Another one is just forgetting to protect administrative pages. Like you can just navigate to admin and boom, you're in. No checks.
Wow.
And the impact, well, remember that big social media breach back in 2019?
Vaguely, yeah.
That was largely down to an API, basically a way applications talk to each other that didn't validate permissions properly. Attackers could just cycle through user IDs and pull out private data from millions of people, direct result of broken access control.
Okay, so it's clearly a huge problem. If you're building something, how do you stop this?
The core principle is deny by default. Assume no one has access unless you explicitly grant it. And this is critical. Always perform access control checks on the server side.
Right, not just in the browser.
Absolutely not. Client-side checks are easily bypassed. You need server validation for every single request. Then you use established patterns like role-based access control, RBAC, in admin, editor, user roles.
Makes sense.
Or even better, attribute-based access control, ABAC, which is more fine-grained. It checks user attributes, resource attributes, maybe even the environment to make decisions. And about those predictable IDs, like 123, 124, use UEIDs instead.
UID.
Universally unique identifiers. They're long, random-looking strings. Impossible to guess the next one. So you can't just increment an ID to peek at someone else's stuff. So yeah, if you're building things, deny by default, validate everything server-side, and really ask yourself, are you relying on client-side checks? Because, well, you shouldn't be.
Okay, powerful stuff. So from controlling who can do what, let's talk about protecting the data itself. A02.2021, cryptographic failures. This used to be called sensitive data exposure. And this sounds really serious, especially when we talk about passwords, credit cards, personal info. You found this affects 67% of applications.
That's right. And it covers data both when it's stored somewhere at rest and when it's being sent over the network in transit. Failures happen when the protection just isn't good enough. Often it's about using weak or outdated encryption algorithms. Think MD5 or SHA-1 for passwords. These are, well, broken. They can be cracked relatively easily now with things like rainbow tables.
Rainbow tables.
Pre-computed tables of hashes makes cracking weak hashes much faster. Another big one is bad key management. Storing encryption keys right in the source code, or in a configuration file that's easy to find, that's a huge no-no.
Right, like leaving the key into the doormat.
Exactly. And then there's transport security, sending sensitive data over plain HTTP instead of HTTPS. Anyone listening in on the network can just grab it.
So like a man-in-the-middle attack, someone sitting between me and the website I'm talking to.
Precisely. They can intercept your login details, session cookies, anything sent unencrypted. Or if developers accidentally commit API keys to a public code repository like GitHub, game over for those services. And the real-world consequences are stark. Think Equifax in 2017, a massive breach. 147 million people affected. Part of the problem was sensitive data stored unencrypted alongside other security failings. The cost was astronomical, financially and reputationally.
So how do we do crypto right? How do we avoid these failures?
Strong, modern algorithms are key. For data at rest, something like AES 256 is standard. For passwords, don't just hash them. Use specialized functions like Argon2, bcrypt, or PBKDF2.
Why are those better?
They're designed to be slow and resource-intensive. That makes brute-forcing passwords, even if an attacker gets the hashes, incredibly difficult and expensive. For data in transit, always use HTTPS, enforced with modern TLS protocols like TLS 1.2 or ideally 1.3.
Okay. And the keys?
Use secure key management systems. Cloud providers offer services like AWS KMS or Azure Key Vault, or things like HashiCorp Vault. Never ever hardcode secrets in your code or config files. Use environment variables or dedicated secret management. What's really interesting, though, is that you can be encrypting but still fail. The how matters. Weak algorithm, bad key storage. It undermines the whole effort. Get it wrong, and you're facing not just data loss, potentially huge compliance fines, like under GDPR or PCI DSS for card data.
Okay, so we've covered access and data protection. What about tricking the application itself into running malicious commands? That sounds like A03.2021 injection. This happens when untrusted input, maybe from a user form, gets mixed up with code or queries and then executed. Found in about 19% of apps, you said. Lower prevalence, but I imagine the impact is severe.
Oh, absolutely catastrophic. Because injection flaws let an attacker directly interfere with the application's backend, often the database or even the underlying operating system. The classic, most famous type is SQL injection. An attacker manipulates database queries, maybe to steal data, modify it, or even delete it. But there's also command injection, tricking the app into running OS commands.
Like rm-rf, wipe the server.
Potentially, yes. Or NoSQL injection for NoSQL databases, LDAP injection for directory services. The common theme is improperly handled input. That famous example of bypassing login using OR11 in the username field, that's SQL injection 101, it tricks the query into always being true.
I recall a case in 2018, a big retailer got hit hard by SQL injection through their search form. Exposed a lot of customer data.
Exactly. It demonstrates how a single vulnerable input point can compromise an entire database. Now, the primary defense, the absolute best practice against most injection, especially SQLite, is using parameterized queries, sometimes called prepared statements.
How do those work?
They fundamentally separate the command logic from the data. The database knows what part is the query structure and what part is the user's input. The input is treated purely as data, never as executable code. It basically neutralizes the attack.
So the database isn't tricked into running the input.
Precisely. Using modern ORMs, object relational mappers, often helps because they typically use parameterized queries under the hood, but you still need to use them correctly. Strong input validation, sanitizing input is also important as a secondary defense.
And the impact if you get this wrong. Data theft, data loss, maybe even complete server takeover. An attacker could potentially dump your entire user database. All right, moving on to A04.2021, insecure design. This one feels different. It's not just about buggy code, right? It's about flaws in the actual plan, the architecture.
That's exactly it. This category highlights that security isn't just something you bolt on later by fixing code bugs. It has to be baked in from the very beginning, at the design stage. Insecure design happens when security considerations are missed early on. Maybe there's no proper threat modeling where you proactively think about how an attacker might target your application. Or maybe security requirements weren't even defined during the design phase.
So like building a house without thinking about locks until after it's built.
Kind of, yeah. It also covers flaws in business logic. Things the code might be doing correctly according to its specification, but the specification itself enables abuse.
Give me an example of that.
Okay, imagine an e-commerce site. The code correctly applies a discount code, but the design doesn't prevent you from applying the same discount code 10 times to the same order, maybe driving the price down to 0. The code worked, but the business logic design was flawed.
Oh, Okay. Or maybe a password reset process that sends a predictable link, making it easy for someone to guess another user's reset link.
Exactly. Those are design flaws. There was a case in 2020 with a financial app. Users could initiate transfers, but the design didn't properly validate the user's session during the transfer process, allowing manipulation. The individual code parts might have been okay, but the overall workflow design was insecure.
So prevention here sounds like thinking about security much earlier.
Absolutely. Threat modeling is crucial. Using frameworks like Stride helps you systematically brainstorm potential threats. Spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. You need to apply secure design patterns, principles like least privilege, defense in depth, built into the architecture. Things like implementing rate limiting shouldn't be an afterthought. They should be part of the initial design to prevent abuse. And this really raises a key question. Is security truly embedded from day one in your development lifecycle? Or is it just a checkbox exercise near the end? Because fixing a fundamental design flaw late in the game is incredibly expensive, often requiring major rework. Way more costly than fixing a simple coding bug.
That makes a lot of sense. Okay, next. A05.2021 security misconfiguration. You said this one is incredibly common, 90% of applications. That's almost universal.
It is alarmingly common, yeah. And it's often about the simple stuff being overlooked. It covers improperly configured systems, frameworks, cloud services, databases, pretty much any part of the stack.
What kind of simple stuff are we talking about?
Default credentials are a huge one. Routers, databases, admin panels often ship with defaults like admin.admin or admin.password. If those aren't changed, well, you've left the front door unlocked.
Right.
Other examples include verbose error messages in production. When an application crashes and spits out a detailed stack trace, that gives attackers valuable information about your internal setup, libraries you use, maybe even database structures.
Yeah, I've seen those. Not helpful for the user, very helpful for an attacker.
Exactly. Also, running unnecessary features or services, leaving unused ports open, having overly permissive file permissions on the server, misconfigured security headers. The list goes on. It's often about not following hardening guides or just neglecting the security aspects of configuration. Especially in complex cloud environments, it's easy to miss something.
There was that big case in 2020, right? A cloud storage bucket, like S3, exposed millions of records just because the permissions were set to public read.
Precisely. A single checkbox in a configuration panel led to a massive data exposure. That's security misconfiguration in action.
So how do you prevent this? It sounds like diligence is key.
Diligence and process, yeah. You need to implement hardening procedures for all parts of your stack operating systems, web servers, databases, frameworks. Disable unnecessary features, remove default accounts immediately, never run in debug mode in production, keep everything patched religiously.
Patching feels like it overlaps with another category, doesn't it?
It does. It overlaps with vulnerable components, which we'll get to. But patching system software is also a configuration aspect. Also, use security headers properly. Things like Content Security Policy, CSP, can massively reduce risks like cross-site scripting by telling the browser exactly what resources are allowed to load. Automating configuration checks with tools helps maintain consistency.
So the takeaway for you, the listener, is really vigilance. Check your configurations. Don't assume defaults are safe. Audit regularly. One simple misstep here can open up your entire system. Okay, that leads nicely into A06.2021, vulnerable and outdated components.
You mentioned the overlap with patching. This is about using software parts libraries, frameworks that have known security holes, right?
Exactly. Modern applications are rarely built from scratch. They're assembled using dozens, sometimes hundreds, of third-party libraries and frameworks. Think of it like building with Lego bricks made by many different companies.
And some of those bricks might be flawed. Precisely. This category covers using components with known CVEs, common vulnerabilities, and exposures. These are publicly documented security flaws. It also includes running older versions of frameworks, like an outdated version of React, Angular, Spring, or Django that lack security fixes found in newer versions. Or using components that are completely end-of-life, EOL, meaning they don't get any updates anymore, security or otherwise.
And we mentioned Equifax before in relation to cryptographic failures, but it's a prime example here too, isn't it? The Apache Struts vulnerability.
Absolutely. That breach was enabled by exploiting a known vulnerability, CVE 2017-5638 in the Apache Struts framework, which Equifax hadn't patched. It allowed remote code execution. A known flaw in a widely used component led to a catastrophic breach. It highlights the risk perfectly.
So with potentially hundreds of these components, how can developers possibly keep track?
Manually. They can't. It's impossible. That's why automated tooling is essential here. Prevention relies on active dependency management. You need to know what components you're using, including their dependencies, what we call transitive dependencies.
Okay, so how do you do that?
Use tools like Dependabot, often integrated with GitHub, or SNEC. These tools scan your project's dependencies, compare them against databases of known vulnerabilities, and alert you. They can even automatically create pull requests to update vulnerable components.
That sounds useful.
Very. You also need software composition analysis, SCA tools. OWASP dependency check is a great open source option. These tools inventory all your components and flag known vulnerabilities, licenses, and outdated versions. And just good practice. Remove any dependencies you're not actually using. Minimize your attack surface.
So what this really means for you is know what's in your software supply chain, keep it updated. That one outdated library you forgot about could be the unlock backdoor into your entire application. Right, let's shift gears to identity. A07.2021, identification and authentication failures. This used to be broken authentication. It sounds like it's all about proving who you are online and how attackers can bypass that. Affects 44% of apps.
That's the core of it, yes. How does the application identify users, and how does it manage their sessions after they log in? Failures here allow attackers to impersonate legitimate users. Common issues include allowing weak, easily guessable passwords, or not protecting against brute force attacks trying thousands of passwords, flaws in session management like predictable session IDs or IDs that don't expire properly, allowing session hijacking. Insecure password recovery, think, what's your mother's maiden name? Security questions. And a huge one nowadays, missing multi-factor authentication, MFA.
I remember that credential stuffing case from 2019 you mentioned earlier. Attackers just used leaked username password combos from other breaches to try logging into a major service. Worked because people reused passwords and there was no MFA.
Exactly. Credential stuffing is rampant because password reuse is so common. Prevention starts with enforcing strong password policies, minimum length, complexity requirements, uppercase, lowercase, number, symbol, and checking against lists of known breached passwords. Don't let users choose password 123.
Makes sense.
But passwords alone aren't enough. Implement MFA everywhere possible. Use TOTP apps like Google Authenticator or Authy, hardware tokens like YubiKeys, or even biometrics. Ensure secure session management. Use long, random, unpredictable session IDs, rotate them periodically, and invalidate them server-side on logout or timeout. And critically, rate limit login attempts to slow down brute force and credential stuffing attacks.
This one feels very personal for listeners. The takeaway for you is turn on MFA wherever a service offers it. Seriously. Use strong, unique passwords for every site. Use a password manager. It's your absolute first line of defense against your accounts being taken over. Okay, now for another newer category, A08.2021, software and data integrity failures. This digs into trust, right? How do you know the software update you just downloaded or the data you receive from an API hasn't been tampered with?
Precisely. This category focuses on failures to protect the integrity, the trustworthiness, and unmodified state of software and data. A big area here is insecure CI/CD pipelines, continuous integration, continuous deployment. If an attacker can compromise the build process, they can inject malicious code into software before it even gets released.
Whoa.
Yeah. It also includes applications not verifying the integrity of software updates or libraries they download. Are they checking digital signatures or checksums? And it covers insecurity serialization. That's when an application takes serialized data, basically, data packaged up for transfer or storage, and reconstructs it into an object in memory. If that data comes from an untrusted source and isn't validated, it can sometimes be manipulated to execute arbitrary code or alter application logic.
So the supply chain attack idea you mentioned earlier, compromising a dependency during the build that fits squarely here, that feels incredibly dangerous.
It is, because it undermines trust at a fundamental level. The most infamous example is the SolarWinds attack in 2020. Attackers compromised SolarWinds' build system and inserted malicious code into their Orion software updates. These signed, seemingly legitimate updates were then distributed to thousands of customers, including government agencies and major corporations, giving the attackers widespread access, a devastating integrity failure.
How do you even begin to defend against something like that?
It requires multiple layers. Digitally sign your software releases and updates using tools like GPG or code signing certificates so users can verify they came from you and haven't been altered. When you consume software or libraries, validate their integrity using checksums like SHA-256 hashes, or checking their digital signatures. Secure your CI/CD pipeline, rigorously strict access controls, auditing, scanning dependencies, and regarding deserialization, avoid it, if possible, with untrusted data. If you must deserialize, use safe, simple data formats like JSON and strictly validate the data structure. Never deserialize arbitrary object types from untrusted input. What's really key here is understanding that your security perimeter extends to your entire supply chain. You need to trust the code in your code and the processes that build and deliver it. It's a complex but critical area.
Okay, almost there. A09.2021, security logging and monitoring failures. You described this earlier as a house with no windows or alarms. It's about not being able to see when something bad is happening, right? Affects 55% of apps.
Exactly. Even with the best defenses, incidents can still happen. If you don't have adequate logging and monitoring, you might not detect an attack for days, weeks, or even months. Or you might not have enough information to figure out what happened after the fact. The failures here include not logging critical security events, logins, successful and failed, access control failures, input validation errors, administrative actions. It also includes insufficient monitoring. Maybe logs are generated, but nobody's actually looking at them, or there are no automated alerts for suspicious patterns, and then there's log tampering. If attackers get in, one of the first things they might try to do is erase their tracks by deleting or modifying the logs.
That 2013 retailer breach you mentioned, where they didn't detect the intrusion for months while millions of credit cards were stolen, that was a logging and monitoring failure.
A classic example, yes. The lack of effective monitoring allowed the attackers to operate undetected for a long time, massively increasing the damage.
So prevention means logging everything and actually watching it.
Pretty much. Implement comprehensive logging for all key security events across all system components. Use standardized log formats. Centralize these logs using a SUM security information and event management system like Splunk, ELK Stack, Elasticsearch, Logstash, Kibana, or others. This allows for correlation and analysis across different sources. Protect the logs themselves, send them to a separate, dedicated, ideally append-only system to prevent tampering, and crucially, configure automated alerts for high-priority security events or anomalous activities so your security team knows immediately when something needs investigation.
So the message for you, our listener, especially if you run systems, is clear. Visibility is paramount. You absolutely need to know what's happening on your systems. You can't respond to a breach if you don't even know it's occurring. Okay, last one. A10.2021, server-side request forgery, or SSRF. You said this one's less common, only 2% of apps, but potentially very high impact, especially in the cloud.
That's right. SSRF is a bit more nuanced, but very powerful in the right context. It happens when an attacker can trick a server-side application into making arbitrary HTTP requests to resources chosen by the attacker.
So the server makes requests for the attacker.
Essentially, yes. Imagine an application feature that needs to fetch data from a URL provided by the user, maybe to preview a web page or download an image. If the application doesn't properly validate that URL, an attacker might provide a URL pointing to an internal system that's normally not accessible from the outside.
Ah, so it bypasses the firewall.
Exactly. The request originates from the trusted server itself inside your network perimeter. Attackers can use this to scan your internal network, probe ports on internal servers, or access internal APIs.
And you mentioned cloud environments. How does it apply there?
In cloud environments like AWS, Azure, or GCP, there are often special internal metadata endpoints. For example, on AWS, http.169.254.169.254 provides information about the running instance, including potentially sensitive temporary credentials. An SSRF flaw could allow an attacker to trick the server into requesting data from this metadata endpoint, stealing cloud credentials, and potentially taking over cloud resources.
Wow, okay. That's sneaky. There was a cloud service breach in 2020 using this, right?
Yes, a well-known case involved exploiting SSRF to access internal metadata, which then allowed the attackers to escalate privileges within the cloud environment. It shows how SSRF can be a gateway to much deeper compromise.
So defenses against this. Seems like validating those URLs is critical.
Absolutely critical. Prevention involves several layers. First, rigorously validate any user-supplied URLs. Don't just check if it looks like a URL, check where it points. Specifically, deny requests to internal IP address ranges like 10.x.x, 192.168.x, 172.1631.x.x, and the loopback 127.0.1. Also, block access to the cloud metadata IP 169.254.169.254.
Use a deny list for IPs.
Actually, a whitelist approach is much better. Only allow requests to specific, approved domains or IP addresses if possible. Deny lists are notoriously hard to get right and are often bypassable. Also, disable unused URL schemes in the library. Handling the request, things like file.gopher.ftp can sometimes be abused. And good old network segmentation helps limit the blast radius if an SSRF flaw is exploited. Don't let your web server talk directly to sensitive internal systems if it doesn't need to. And this brings up a crucial point, especially for cloud users. Are your instances properly isolated? Can they probe internal resources they shouldn't? SSRF really highlights how a vulnerability in one application can become a pivot point into your broader infrastructure. It's a subtle but potent threat in our increasingly interconnected, cloud-centric world.
Ooh. Okay, that's the full OWASP Top 10 for 2021. We've covered a lot of ground, from basic access control all the way to subtle server-side forgeries. It really drives home how multifaceted web security is.
It really does. And the key thing is that these aren't 10 completely separate issues. They often overlap and interact. Addressing them requires a holistic approach. Secure coding, yes, but also secure design, rigorous configuration, continuous monitoring, and awareness of the entire software supply chain.
It's clear this list is an incredibly valuable tool, a framework for thinking about these risks.
Absolutely. And remember, knowledge is only powerful when it's applied. These principles need to be part of the culture, integrated into every stage of development, and constantly revisited as threats evolve. It's not a one-time fix.
And for you listening, whether you build software, manage systems, or just use the web every day, understanding these risks helps you stay safer online. It empowers you to ask the right questions and demand better security from the services you rely on.
And maybe a final thought to leave you with. The OWASP Top 10 reflects the current landscape based on extensive data, but threats are always evolving. As we move towards more complex systems, maybe more AI-driven applications, how might these fundamental weaknesses, flaws in access control, data handling, integrity, visibility, manifest in new and unexpected ways? And how can we start thinking now about anticipating those future threats?
A challenging question indeed. Thank you for joining us on this deep dive into the OWASP Top 10. Until next time, stay curious and stay secure.